Hello. I think we're ready. Do you hear me and see the desktop and all that? Everything seem okay?
Yes.
Okay, great. Thanks. All right. Okay, we're gonna pick up where we left off, trying to understand why closures are important. So last week we did a whole bunch of examples. I mean, I put all the code up there. We did all these examples in C, and we used the language 7, C, and JavaScript, and we were kind of comparing. And the ones where language 7 didn't use closures, and the ones down here did use closures. And what I want to show you today is more examples of like how closures are important, and in particular, something called curried functions. Uh, this is an idea, not curried chicken, curried functions. there's uh there's this idea of currying functions, and it's not named after, it has nothing to do with curry in cooking. It's actually named after a mathematician named Haskell Curry. It's the same person that the Haskell programming language is named after. So the the idea of currying functions comes from Haskell, this guy Haskell Curry. It's just really really quirky that his name is, like the like food. So we talk about curried functions, and they're really important. They become really important. Yeah, and he was important enough that his first name became the name of a programming language, and his last name became a name of an important technique. So he's really unique. I think he's the only person who has two ideas named after him like that: his first name and his last name. Okay, so we want to talk about what we mean by curried functions, because they become, if you Google curried functions, you'll see massive stuff written about them, and there's a lot of misunderstanding. Is another one like closures. There, it's currying functions is very, it requires, it's an application of closures. Currying functions is an example of a thing you can do once you have closures. Okay, and it's used a lot in the ML programming language, and it's being used a little bit in JavaScript. Currying is an example of a pretty sophisticated technique that isn't moving easily into other programming languages. So like Java, C++, Python, JavaScript, they're all adopting closures and a lot of ideas from functional programming. Currying is a little bit harder for them to adopt. Okay, but JavaScript has adopted it a little bit. So it's worth talking about because it's a really interesting, elegant idea of what you can do with functions once you have closures. Okay, so um, the starting point is our function MakeAdder that we did last. So the starting point, oops, not there. We've done it for a little. We've done this function several times now, but this function here, well, here it is in language 7, and here it is in JavaScript. Yeah, here's our MakeAdder. This is MakeAdder in language 8, and this is MakeAdder in JavaScript. Okay, so I want to play with these examples here. Okay, and show you that there's another way. We were thinking of this as a um, method factory. You call MakeAdder and it gives you back a function, and that's an important idea. Function factories are pretty common design pattern in functional programming. Okay, so comparators are examples like that. Comparator functions, you use them when you do things like sorting or finding the max or min of a list, and it's not unusual to write a function that creates comparator functions. So uh, a, a sophisticated library of sorting will have the sorting algorithm will take a comparator, but then you'll have functions that build comparator functions. And maybe next week we can look at some examples of that. But function factory is not a bad idea. But now we want to change our point of view. There's another way to think about MakeAdder that's really different. Okay, so you can think of MakeAdder as a curried function, but that's what we want to talk about. Is how can I think of MakeAdder is not, instead of thinking of it as a function factory, I want to think of it as a curried function. Okay, so the starting point is to think a little bit about math functions. Okay. Here's a real simple math function. Takes 3 parameters. I'm just going to add them together. Okay. There's a real simple math function. Okay. Now, here's a kind of a funny idea. In math, every once in a while you'll see a notation like this. You don't see it very often. What that means is think of the function f with a 5 in the x slot, but y and z unspecified. So in a sense, you're thinking of it as 5 plus y plus z. Okay? That essentially is a function of 2 variables. Okay? So if you take a function of 3 variables and you give one of the variables a value, but not the other 2, you get left with a function of 2 variables. Now, this notation is actually used in a few places in math, but not very often. Okay, but this is the key idea that if you have a function of several variables and you give one of the variables a value, you still have other variables left, and you can think of that as a new function. Okay, then, for example, you could take g of something like this. That would be the same thing as, well, I'm sorry. Well, here's a function h of x, which I get by taking, I'm sorry, h of y. I get this function by taking my g, putting a value in for the z. So this would be the same thing as f of, okay, there's a 5 in for the x. The y is left unspecified, and there's a 7 in for z. Okay, so that would be the same thing as 5 plus y plus z. Okay, you can do weird things like this. So I've got this function g, or I've got this function f. In a sense, I've now specified the x and the z, and I've left the y unspecified. So some mathematicians use a dot to mean fix this variable and leave this one unspecified, leave this one unspecified. So that leaves these two as new variables. Okay. I mean, you could even write this, instead of using the dots like some people do, you could just write it this way. Okay, it's f with a fixed number here, and this y gets carried over to here, and this z gets carried over to here, and then they get plugged into the formula like this. Okay, so another way to write this one, if you don't like the dot notation, you can say, we'll say that there's the y, and the y goes there. Okay, so h of y is g of y comma 7, which is f of 5 comma y comma 7, which is then this, whoops, there's a 7 there. Okay. Okay. Now this is getting, the idea here is that if you have a function of multiple variables, you can give one of the variables a parameter. Okay. Now, by itself like this looks a lot like default values. Okay, like there's a lot of languages that let you do things like I could do Python lets you do this. So go back up here and say f of x equal 5 comma y comma z equal 7. Okay, equal x plus. Okay, some languages let you do this. Now, if I do that, then f of 4 means, well, this variable didn't get a default value. Since there's only one value here, it goes into here, x gets 5, z gets 7. Okay, that's a little bit like this h. Okay, so f of 4 is a little bit like saying h of 4. So f of 4 is kind of the same thing as saying h of 4. Okay. This doesn't lead to the idea of currying. They look a little bit alike, but this leads to the idea of currying. Okay, so this idea of the key idea is I want to have this idea of a function of multiple variables, and I want to give certain variables values, but not other variables values. Okay, but I don't want to do it with default values. I don't want to do it like this. For example, if you defined a function this way, you can't, like, if I pick up on this idea here, I can define another g. I could have defined g a different way. I could have given I could put a 9 in here. Okay. And I could have put 3 in here. So I have a different h here. Okay. So I can get all kinds of different h's here. When you use the default value way, that's the default value is fixed. So this f can give you that h of 4, but it can't give you this other. Here's another h of 4. That's a different h of 4 now. Okay. This h of 4 is not the same thing as this one. But there's nothing I can get different h of h's, but I can only get one thing out of this. This isn't very versatile. This is kind of convenient, but it's not very versatile. Okay, so default values is not the same thing as curried values. Okay, all right. Now, but so the real important idea is to give a function some of its parameters and not others. Okay, now when you do this, the tricky thing is to think about this thing as, okay, you start with this function, and then you think of this as like a function factory, where this is giving you back a new function. See, this is where this guy can act like a function factory. If you give one of the parameters a value, it gives you back a new function. Okay. Okay. So let's do it down here a couple times. Here's a function. I can think of this guy as a function factory, like MakeAdder. Okay, so here's a function. H of x comma y is going to be f of x, y, 10. Here's another function. G of x, y could be f of x, y, -1. Okay, I built two. I'm thinking of this as a function factory. What this is you put a 10 into z, so that leaves two variables free. So this thing gives you back the function x plus y plus 10. Okay, think of that as a function created by this guy. Okay, or here, think of this as x plus y plus -1. Think of this as a function created by this guy, and this is a name for that new function. So think of this as a function factory. Okay, another one, k of y. It's going to be, I'll make it f of 3 comma y comma 12. Okay, that's 3 plus y plus 12. Think of this as this guy now has produced a new function. This function has produced a new function that I'm calling by this name. So think of this thing as being able to produce new functions. So think of a function of 3 variables as a function factory. It can produce functions of 2 variables. It can produce functions of 1 variable. Okay. Now, if you give it, I mean, if you do f of 1, 2, 3, there's nothing. It doesn't give you back a function. It gives you back a number. Okay. So you give it. These are called partial applications. You give it some parameter, maybe one parameter, maybe two parameters. That's called a partial application. If you give a function of several variables a partial application, it gives you back a new function. So think of functions as function factories. So every function of two variables now becomes a function factory. Every function of three variables is actually a function factory. So I can go down here and say, oh, f of x, y is x times y. There's a function of two variables. Okay, now I can think of it as also a function factory. And I can say g of x is f of x comma 10. Okay, now I've got the multiply by 10 function. Okay, so I can think of f as a function factory. It produces functions of one variable. It can produce a bunch of different functions of one variable. I could even do the following. Well, okay, yeah. So g, since x and y, since x times y is y times x, it doesn't matter if I do this. I get the same function. So this is, in a sense, this is not a great example. Those are really the same function. I could pretend they're different by giving them different names, but G and H are really the same thing. Okay, but that's because this thing's commutative. If I used a more interesting, like even if I did even just like this, okay, now they're not. Okay, now this is 10 minus x, and this is y minus 10. Okay, so now they're not the same function. Okay, so f of xy is x minus y. So g is subtract its variparameter from 10. H is subtract 10 from its parameter. Okay. So I think of f as a function factory that can produce functions for me. Okay. Now, mathematicians have kind of thought this way, but they never really formalized this until Haskell-Curry came along, and he said that this is kind of a clever idea, and it should be formalized. This idea that a function of more than one variable can be thought of as a function factory. He thought we should actually formalize that idea. Okay, and he formalized it in kind of a clever way. And this was before programming languages even existed. This was actually, he did this before any programming language existed. He was working in logic, and he just thought, he was thinking about functions and thinking about what they implied about the logic of mathematics and how they could be used in logic. And he came up with this idea that this idea that one function can produce other functions for you, we should make that kind of concrete. And then when he made it concrete a few years later, when they started inventing programming languages, they realized that that was a real clever thing, that they could put, if you built this idea into a programming language, you could do some very clever things with it. Okay, so a currying really just means a function of several variables where you do a partial application of a function of several variables, which produces a new function. So currying is a partial application of a function of several variables that returns a new function. Partial application of a function of several variables. Now, partial application means you don't give the function all its parameter values. So partial application means if you have a function of 5 variables, maybe you give it 2 of the variables. If it's a function of 3 variables, maybe you give it 1 or 2 of the variables. So partial application of a function of several variables. It doesn't, with function of 1 variable doesn't have a partial application. So a partial application of a function of several variables that gives you back a new function. That's what we kind of mean by currying. Okay, but we want to make this real formal. Okay, right. So one trick to this is to change notation, to stop using these parentheses. Okay, so write functions this way: f of x, y, z, like that, equal x plus y plus z. no parentheses. Just write the function this way, okay? So use a different notation for functions. That's the first step, is to get rid of this idea of parentheses being wrapped around the parameter values. Okay, that's going to help make the notation a little bit cleaner. Okay. Then, well, let me do this with a function of one variable first. So f of x will be, say, x times x. So this is the f of x is x times x. So f of 4 is 16. This is a function definition. Okay, and this is a function application. No parentheses. When you define the function, you put the name of the function followed by the parameter. Then when you call the function, you put the name of the function followed by the argument. Okay, so then f of x, y, z is x plus y plus z. That's my function definition. Okay, and then f of 1, 2, 3, which is going to give me back 6. That's the function application. Okay, now here's where his idea got real clever. That's a partial application. Okay, see that instead of having to use this funny dot notation or funny things, that's a partial application. That says f with x equal 1. But what that gives me back is a new function. So this is going to give me back a function of 2 variables. Now, that function doesn't have a name, but it's going to give me back, I'll write it as a lambda expression. This is going to give me back a function y comma z goes to 1 plus y plus z. So this is a partial application of the function of 3 variables. It puts the parameter in there, but then it gives me back a function. I want, and this is what Curry said, from now on, it's going to be automatic that if you give a function up, if you do a partial application, you get back the function that's left. Now, by coming up with this notation, what he gave up was the ability to do a partial application on, say, the first and third parameters. See how over here I said k of y is f with the first parameter being 3 and the third parameter being 12. If you do this, I can do the following. F of 1, 5, but that's going to give me back a function that's a function of z that takes in z. I'm using the lambda expression notation. It's a function of z that takes in z and gives me back 1 plus 5 plus z. You can only do partial applications in the order that the parameters were given. I can't do a partial application on x and z and get back a function of y. Okay, like I did up here. I did a partial application on x and z and got back a function of just y. In this clever notation, which is the notation that modern language, like languages that do curried functions, they use this notation of Curry's. It makes things very elegant. The only thing you give up is being able to do a partial application on the first parameter and the third parameter, which you can do with this dot notation up here or with this kind of notation here. Okay, so this is a partial application on 1 parameter, the first parameter. This is a partial application on 2 parameters, and it gives me back this case I get back a function of 1 variable. This case I get back a function of 2 variables. If I want, I can do the following. I can say h of y z is f of 1. Now this is actually pretty neat. See, this notation is really pretty. It's starting to get kind of abstract now. See, f of 1, we said, gave us back a function of 2 variables. Well, that's what h is. H is a function. I'm just giving a name to this guy. H of yz is the result I get back when I take f of 1. Okay. In fact, you can even write this as just this way. H is that function. H is what you get back when you give f one parameter. Okay. And maybe I'll let J be f of 1, 5. So now J is the function of one variable I get back from partially applying these two parameters to f. Okay. Okay. Now, let me show you a language that actually does it this way. So you can see that this is really done. And then we'll go back and see how this relates to JavaScript and the MakeAdder. Okay, now here's a programming language called ML. ML is essentially this language that I'm using starting here. I'm sorry, starting here. So for example, I would say here that function f of x equals x times x. Okay. Then f of 4 is 16. Okay. So I'm using the notation that Haskell invented without any parentheses. So the function f with the parameter x, its definition is x times x. Then call f with parameter 4. Call f with parameter 5. Okay. Now here's a function f of 3 parameters, x, y, z. And it's going to be, I'll make it x plus y plus z. Okay. F of 1, 2, 3 is going to be 6, you know. But what's f of 1? F of 1 is here's what this, I kind of skipped over to the notation. F of 1 is a function. It's a function of 2 inputs and an output. Because that was, I gave it the 1, which was actually the x. This is the y variable. This is represented by, represents the z variable, and this is the return value. If we go back up here, I said function f of x is x squared. And ML came back and said, well, f is a function that takes in an integer and gives you back an integer. Okay, so so that was how it translated this. This is a function f. See, so the variable f is a function that takes in one integer and gives me out another integer. Okay, when I apply f of 4, I get back an integer. When I take f of 5, I get back an integer. Now look at f of x, y, z. It's a function that takes in 1, 2, 3 numbers and gives me out a number. Okay, so f is now a function of 1, 2, 3 inputs and an output. And if I give it 1, 2, 3 inputs, I get back a. Okay. But notice if I give this function only its first input, it's still going to give me back the function of 2 inputs and 1 output. See, that's what happened. When I give f just its first input, ML said, that's fine. You gave me 1 input, so I give you back the function of 2 inputs and 1 output. That's what it did. Now, if I want to, I can say G, I can say val G. I'm going to give a name to this guy, f of 1. G is a function of 2 inputs, G of 3, 4. That's 1 plus 3 plus 4, that's 8. See, G is the function that adds 1 to its 2 input parameters because it was the partial application of f to its first parameter. Okay, so there was the partial application of f to its first parameter. In a sense, every function is a function factory. So when I give f 1 parameter, its factoriness of it is it produces a new function of 2 parameters. The 2 parameters I didn't specify. Yeah, if I say f of 1, 2, I get back a function of 1 parameter. 1 goes into x, 2 goes into y, and the z, this int here is really the z parameter, the third parameter. If I want, I can give this guy a name. I can say val h is f of 1, 2. Okay, h of 5 is 1 plus 2 plus 5. Okay, that's 8. H of 5 is 1 plus 2 plus 5. Okay, so I'm using the fact that every function of 3 variables is really a function factory, that if you give it only some of its parameters, it gives you back new functions. Okay, and this is called curried. When functions are naturally function factories, they're called curried functions. Okay, when you can partially apply any function and automatically get back a new function. So when every function is by definition a function factory, then you say the language has curried functions. And only a small number of languages do this. Haskell, ML's one and Haskell's another. JavaScript kind of tries to do this. I'll show you how JavaScript can almost do this. And JavaScript's not bad. It's not too bad at how it does this. Java and C++ really have a hard time with this. I don't think, like if you look up, you can see there, people will talk about currying in these languages, but if you read about them, you'll see that they're not doing it in anything like an elegant way. They're doing something that's kind of like currying, but it's not really at all elegant. Because they don't have this really nice notation that we have here. The key is this notation that drops the parentheses, so that you don't have to like say f of, like here, h of xy is f of, well, the advantage of the parentheses is you can say where the x and y go. You could put the x in the first and third slot if you wanted to. Here, I put the x and y in the first and second slot. But like here, the y went into the middle slot. Yeah, the one variable here went into the middle slot here. When you do it down here, if you give it one variable, it's got to go in the first slot. If you give it 2 variables, they have to go in the first 2 slots. You can't skip around on the partial application. You can't take f and give it x and z and leave the y ungiven. That's the elegance of the notation is works very nicely, but what it gives up is the ability to kind of like skip around in saying, I want to fix 3 and fix y, z, and leave y free. Okay. Notice that this notation is a lot busier than this notation. See how simple that is. Yeah, you just say things. Yeah, look how simple that notation is. G equals f of 1. Here h is f of 1, 2. Yeah, it's just a very unbusy, very simple notation. It takes a little getting used to. That's saying f takes, f's first parameter is 1, f's second parameter is 2. F really took in 3 parameters, so that means now f's going to give me back a function of 1 parameter. So h is going to be a function of 1 parameter. You need to know what you're reading when you read these curried functions, but once you're used to them, they're really they're very easy to read and very easy to work with. Every function becomes a function factory. Okay. Now, if you go back to our okay, now let me show you one more step in this. When I wrote the function this way, I said function f of x, y, and z is x plus y plus z. Okay. That's ML's simple notation. But here's what I'm really doing. And this notation here is the longhand definition of what I just did. And what I'm going to do, I'm going to give it a different name, but this is going to be the exact same function. I'm going to call it G. Well, actually, let me, no. I got ML mixed up now. There. Okay. Okay. Let me say F1 of x, y, and z is x plus y plus z. Okay. Oh, I forgot. Function f1. Okay. Now I'm going to define function f2, but because I'm going to define it a different way, I use a different keyword. Instead of using the keyword fun, I use the keyword val. Okay. So I'm going to say f2 of x is, now remember, if you gave function f1 its x, it gave you back a function of 2 variables. So what I'm going to say is that if you give f2 of x, it gives you back a function of y. And if you give y a value, it gives you back a function of z. And it gives you back x plus y plus z. Here I'm formally saying that f2 takes in a number and gives you back a function. And that function takes in a number and gives you back a function. Oh, what did I do wrong? Oh, I'm supposed to put an arrow here. It gives you f2. Let me start over again. f2 is a function that takes in a number and gives me back a function that takes in a number and gives me back a function that takes in a number and gives me back x plus y plus z. Okay? My f1 and my f2 are actually identical. They're the exact same thing. Okay? I messed that up. So let me do it all over again. So f1 is f1, the function f1 of x, y, and z is x plus y plus z. Okay, now that's a curried function. So that's really a function factory. Now here's the way to spell it out in precisely. f2 is a function that takes in one number and gives you back a function that takes in another number and gives you back. Now see, that's what's, if you give f1 5, it gives you back a function of y and z. But if you give it 5 and 6, it gives you back a function of z. Now, if you give f1 5, it gives you back a function of y and z. But if you give that new function 6, it gives you back a function of just z, because every function is a function factory. So the function you get back by giving f1 5 is still another function factory. So that's what this is saying. f2 is a function factory. f2 is it's a function that takes in x and gives you back a function. And that function takes in y and gives you back a function that takes in z and gives you back now the x plus y plus z. Okay. And from ML's point of view, what I wrote here is really just a shorthand notation for what I wrote here. This is what a curried function is. A curried function is a function that returns a function. But that's exactly what MakeAdder did. See, this is MakeAdder with 2 variables instead of 3 variables. Okay. If I just change my names a little bit, I would say function MakeAdder of x, y is, well, the way we did it, we said MakeAdder as a function of x. And I'll write it this way. MakeAdder is a function that takes in an x, and it gives you back another function that takes in a y, and it gives you back x plus y. Okay. Now I'd say val add 5 is MakeAdder with 5. Okay. Add 5 to 6, get 11. Add 5 to 7, get back 12. Add 5 to 2. See, I built the, then I could build add 10 is MakeAdder with 10. Oops. Oh, I forgot to say val. So add 10 is the result of MakeAdder with 10. Okay. So add 10 to 6 is 16. Okay. So so now MakeAdder is a function factory that builds these adder functions. But MakeAdder has the exact same syntax as this function of 3 variables. MakeAdder just is a function of 2 variables, x and y. But that's not the way we thought about it. We thought about it as a function factory. So if you go back to, see, we said function MakeAdder takes in an x, and it returns a function that takes in y, and then it returns x plus y. So MakeAdder, but see, it was just a function of 2 variables, x and y. But it was essentially, this is a curried function of 2 variables. There's the function with only 1 parameter, and it gives you back the function of the other parameter. There's the function with the x parameter, and it gives you back the function of the y parameter. So this function factory idea is essentially curried function. It's an example of a curried function. There are lots of places in functional programming where you use function factories that aren't mimicking curried functions. It's just that curried functions are an example of this idea that every function, that a function can return a function. A function can return another function. A function can return another function. Okay. What currying does is does this automatically. Currying says, if I define my function this way, it's really been defined this way behind my back so that it's acting as a function factory. So if I give it only 1 parameter, it gives me back a function. Okay. If I give it 2 parameters, it's still going to give me back another function, but now a function of 1 variable. So every time I define a function, the function is automatically built up in this curried way, which means it's automatically built as a function factory. Okay. So the language just does, you don't even have to know that. When people are first taught ML, they just taught this notation. If you want a function of 2 variables, you say function g of a, b is, and then you just do what you want. 2 times a plus 3 times b. Okay. There's your function of 2 variables. You don't need to even know that it's been curried. Yeah. And then later you're taught, well, if you do this, if you say if you call your function g with only 1 number, that makes sense. It's not an error. Oh, see, in Java, if you define a function of 2 variables and you only give it 1 variable, you get a compiler error. See, this is another way to think about how profound this is. In a language like Java, if a function is taking 2 variables and you give it only 1, you get a compiler error. Now, in Java, because you use the parentheses notation, it's really hard to give a function of 2 variables only 1 variable. See, if you have a function of 2 variables like g of x of a, b is 2a. Yeah, if you think of it like this, it's kind of hard to say g of 2. You just say, well, wait a minute, that doesn't make sense. You said that g takes in 2 things. Yeah. If you say g of 2b, kind of that's what you maybe meant. It just you get a syntax error. Yeah. Well, let a be the 2, b, I'm not saying what it is yet. Yeah, give me back a function. Java just doesn't work that way. And the parentheses notation kind of force you to think of, this is a function of 2 variables, so you got to give it 2 things. That's one of the reasons why they got rid of the parentheses notation in languages like Haskell, because now this function of 2 variables isn't really a function of 2 variables. It's really a function of 1 variable that produces a function that takes in another variable. It's really a staged kind of thing. G takes in 1 variable, But then after it's taken in that one variable, produces a new function that then takes in the second variable. So it's okay to give G one variable, one argument. It's okay to give G one argument. It gives you back another function. Okay. And then if you want, I can give that guy a name. I can say, well, K is G of 4. Okay. K is the thing that takes, well, now that K is, so K of 1, you can figure out that that was, the A was a 4, so that's 2 times 4 is 8. Then K was taking in the B, so 1 times 3 is 3, 8 plus 3 is 11. Okay, but the 2 times 8 is built into K. K remembers this. The remembering of this 4 is where the closure comes in. See, K has to remember this parameter of G. And if we look at this from the right point of view, what we're doing is, well, that's what we saw. MakeAdder was the whole point of MakeAdder was to introduce closures. That when you return this function, it has to remember that guy in its closure. This function is open. The x is a non-local variable. This function has a non-local reference that's closed by this one. Okay. In our curried functions, when I do this, f of 1, that's plugging a 1 into here. This function has to remember that 1. It has to carry it somehow. That 1, which is in the x, has to be carried along somehow, and that's done by a closure. This is carried into closure. It's not literally there. It's still going to be x plus y plus z, but then there's along with this, you might think of this as a closure x equals 1. I mean, that's actually kind of what it becomes. F of 1 is really a pair of things. It's the new function with the environment that says how to close off that variable there. Then this one would be two things. See, the environment would hold two bindings now. So this is really two things. The formula, z goes to x plus y, with the closure that remembers that x is 1 and y is 5. So the function is really that guy and that guy. That's the closure. An IP-EP pair. The code and the environment. The code and the environment. An IP-EP pair, which is a closure. So an IP-EP pair, which is a closure. Almost nobody calls them IP-EP pairs anymore. I mean, some compiler books, I think, still might use that phrase IP-EP pair. I really like it because I think it helps remember what closures are. Closures are, the word closures is very mathematical. It's the idea that this is an open expression, and you have to close it off. The expression, this is an open expression. The y is bound to that y, the z is bound to that z, x is unbound. Since x is unbound, that's an open expression, so you need to close the expression. That's kind of an abstract thinking. IP-EP pair is what it is. The closure is a pointer to the code and a pointer to an environment object that holds the binding for the extra variable. In this case, x is 1. This guy is a closure. So he's a pointer to the code. The code is the same code as this. It's that code there. It's still that code there. In fact, you don't even really need that part there. You could kind of go like that. It's that code with that binding. It's that code with that binding. Yeah, depending how you want to think about it, you can think of it as, or yeah, it's probably it's harder to say which way it's really better to think about it as that. Oh, you know, that lambda expression that's open with that closure, or that lambda expression, that's the code, that lambda expression which is open with that closure. Okay, lambda expression that's open with a binding, lambda expression that's open with a binding. Okay, and ML is doing this stuff for you automatically. I mean, well, JavaScript, now JavaScript, notice JavaScript has closures. So here's the interesting thing. If JavaScript has closures and we can write MakeAdder, can we do what we're doing over here? Can we do what Haskell does? Can we do something like this? Okay, and the answer is almost. The answer is almost. The answer is you can almost do it. Okay, actually, let me switch to JavaScript and see what we can do. To switch to JavaScript, I'll just do F12. There's the JavaScript console. And just like I have the ML REPL over here, now I got a JavaScript REPL over here. And I can just, if I can remember my JavaScript notation well enough, I've got function f of x, y, z is x plus y plus z. See that? Is that right? JavaScript's got so many different notations. I'm trying. JavaScript has too many notations. Now I'm function. Does anybody remember? Let's see. What am I doing wrong here? Unexpected token equal. Oh, yeah. You just. Function f of x, y, z is, yeah, you don't put an equal sign between the function and the body, okay? Now, this is an uncurried function, f of 1, 2, 3, okay? F of 4, 5, 6, okay? F of 2, 3, not a number. See, I get it, yeah. It didn't like that. It didn't give me a compiler error, but it's putting 2 in for x, y for z, it's putting 2 in for x, 3 in for y, and it's actually leaving z undefined, and it's trying to add 2 plus 3 plus undefined and getting not a number. That's kind of the quirkiness of JavaScript, but it didn't curry them, okay? But I can define this function curry to see if I can do it, if I can remember the syntax. So I want function f of x to be return. The notation is going to be kind of horrible. Function of y that return function of z that returns x plus y plus z. Now let's see. Close. Oh, I need a semicolon there. I don't know if I need more semicolons in this or not. F of 1 is a function. See, I've curried it. I wrote it out in I wrote it out in over here in ML. Remember, I could write it there was a nice way to write it. F1 is F1 of XYZ is X plus Y plus Z. That was equivalent to what I wrote here in JavaScript. F of XYZ is return X plus Y plus Z. Okay. So now ML took that and gave me for free this curried version, which was what I called F2. ML gave me the curried version automatically. JavaScript doesn't give me the curried version automatically. But see what I wrote here? Looks a lot like what I wrote here. F2 is a function that takes in an, let's see. F2 is a function that takes in an int. And it returns a function that takes in an int. And it returns a function that takes in an int. And it returns X plus Y plus Z. ML automatically turned this guy into that guy. Over here in JavaScript, I have to turn this guy into this guy. The function of X that returns the function of Y that returns the function of Z that returns X plus Y plus Z. If I give my function one of the parameters, I get back the function of Y and Z. If I give this function, now here's how I do it. F of 1, 2. I got the function of Z. F of 1, 2, 3, 6. Now, see, that's why the people in Haskell land got rid of the parentheses. First of all, see how ugly that is. I have to write F of 1. That's a function that took in one parameter. It gave me back a function. Then I fed 2 into that new function. But I had to use the parentheses to say feed 2 into the new function. That gave me back another function that I have to feed 3 into. So I have to write, instead of writing elegantly, instead of writing F of 1, 2, 3, JavaScript doesn't know squat what that means. It's got to be that. F of 1, of 2, of 3. Yeah. And then I could do F of, I could do F of 3, F of 1, F of 4, Notice I have to do them in order. I can't somehow curry the Y and the Z and leave X free. I have to curry them, just like in ML, they have to be curried from left to right. You can partially apply this. You can do F of 1. Okay. And just like over here, I can do F of 1, but I get back the function of Y and Z. Over here, I got back the function of Y and Z. Notice that here, it doesn't even tell me that they're Y and Z. Here, it's a little bit more abstract. Here, JavaScript's saying, oh, you're getting back a function. Now, oh, notice that this guy here, the X, whoop, I didn't want that. I don't even know where I am now. I'll go back to the console.
Estamos ahora en la generación de público.
Okay. So see this X? That's the thing that's the closure. Okay. The closure is, now notice that that's no hint of that here. If you want to see that there's really a closure here, you have to do this, console, log dot, what was it? Log, something weird. I should be able to remember it. Log, oh, I put it in the website. Is no, not log, console.dir. It's just really weird, I think. So you say console.dir. I have no idea what the dir even stands for here. And then say F of 1. Okay. It tells me it's an anonymous function. Go down here. It's got scopes. There's the closure. X is 1. See, there it is. There's exactly that notation that I was using over here. It's the function. It's that function with the closure X equal 1. And over here, they do it, they actually show it to you kind of nicely over here. okay? F of 1, if you dig deep enough, you have to kind of go through a few little triangles. Then here, it's a closure of F with the pair x1. It's the closure of that with the pair. It's this closed off with x1. Now F, yeah, here they don't show you, F is up here. It's that, F is that. So actually, if you open this up, oh, it just shows, yeah, see now it's not telling you what F is. So it's telling you what the closure is, but it's not telling you what F is. And then the F itself, I guess you have to go up here. That would be oh, let's see. Boy, if you're not familiar with this stuff, you can be, digging for the, like the formula for F should be in there somewhere. It's that function with that environment. Okay. Now the closure says it's this function with this environment, but now you want to know what that function is. I'm not sure which one of these has got the function buried in it somewhere. Offhand, I'm not sure which one. God, there's a ton of these. I mean, we see it up here. Yeah, there's the function, but it's in here somewhere. It's a function of y. It's a function of y that returns a function of z, and it's got x closed over. So when we give f1, remember, when we give f1, if we go back up here, when you give f1, it returns this function of y. So there's the function it returns. So it gives you back a function of y that gives you back a function of z. So the function of f is an anonymous function that returns, that takes in a y parameter. And I don't, you should be able to, it's kind of quirky that it shows you the function nicely here, but it doesn't show you the closure. When you get down here, it shows you the closure, but now I'm not even, I'm having trouble figuring out where they're hiding the function definition somewhere in here. Maybe here? Wow. No. You could try opening everything, but there's hundreds of these guys. And every time you open one, it opens hundreds more, because every object is an object, and look how deep you can. It's weird. You expect this to bottom out at some point, because how could JavaScript keep doing this forever? But it just keeps going and going and going and going and going. The language is not elegant. There's just something really wrong about this. Okay. I mean, this is just a trivial little example of a curried function, and there's just something really wrong about it. This is bizarre. And I haven't even opened up a fraction of these things yet. I mean, how can this all be? Notice that all this is under just this one arrow here. That arrow, look at it. And I didn't even open, I'm only opening a fraction of its sub arrows. There's something really, JavaScript's really strange. JavaScript's really strange. I have a feeling that some of these arrows are just pointing to each other, so that maybe this will actually go forever. There might even be circular chains here, because how else can I could just keep going and going and going and going and going? Look, I can just keep going. How could this go on for can this go on for hundreds of steps? How much memory would this be taking? This is bizarre. Oh, there's something that ended. There, I opened one of those little triangles and there wasn't another triangle inside of it, but all these others, boy, look. it almost seems like it's never going to end. I wonder if it's circular. I wonder if JavaScript is somehow doing kind of like just building circular lists, which that would explain why these kind of go forever. And it just never traverses the circular list, but it's actually possibly building a circular list. Because look, this just keeps growing and growing and growing and growing, even though it's a trivially simple object. Look at that. That would lead me to think that the JavaScript's actually building a circular list. And I'm just going around and around in a circle in a circular list and don't realize it. But why in the world it would do that? Either it's building a circular list or somehow it's managing to store a massive amount of data for even a simple function. This is pretty weird. Okay, and these things could probably just go on. Yeah, wow. I'm betting on circular list. So I'm betting I'm going around in a circle here and chasing my tail and just don't realize it. But that begs the question of why would the interpreter be building circular lists to represent functions? Okay, but all that's just under this. That's what's inside that anonymous function. The only thing we really care about is this closure. Okay, now that's not very deep. See, open the anonymous function under scope is where they store the closure. They store this closure under scope. Okay, all right. So curried functions use closures. Essentially, we're back to just this MakeAdder. It's this MakeAdder idea, but done for you automatically. So as soon as you define a function of two variables, so you define a function of two variables, I'll call it, function Bob of u, v is, whatever I wanted to do with u and v. I mean, I could think of u and v as lists, so I could say, okay, in this case, I could say u concatenated onto v. There's a function of two lists. Okay, so now Bob of the list 1, 2, 3, 4, that's the function that takes 1, 2, 3, 4 and concatenates it to anything you want. So I can say Alice, I can say value Alice equals Bob of 1, 2, 3, 4. So now Alice is going to append 1, 2, 3, 4 to any list you give it. So if I say Alice of 10, 11, 12, so I get 1, 2, 3, 4 put in front of 10 and 11, 12. Alice is partially applied Bob. Okay, you give Bob one list and then you can give Alice the second list. Now I can say, Alice of 7, 8, 9, and I get back 1, 2, 3, 4, 7, 8, 9. Okay, and then if I want to, I can create an Alice 2, which is Bob partially applied to 10, 20, 30. Okay, Alice 2 applied to 1, 2, 3 is going to take 10, 20, 30 and put in front of 1, 2, 3. Oops. Oh, what did I do here? Oh, what did I do wrong? Oh, I misspelled it. How did I spell it? Oh, I had an extra semicolon here. Yeah, I missed. Oh, I forgot the equal sign over here. I forgot the equal sign here, and I didn't spell that right. There. Okay. Alice 2 appends 10, 20, 30 in front of any of its list. ML automatically turns every function of several variables into a curried function of several variables. In the world of JavaScript, there's a small number of libraries that are currying their functions of several variables. So they're actually writing that instead of that. There are some libraries in the JavaScript world that say, let's curry our functions so that you could partially apply them. Okay. And then they're trying to come up with interesting syntaxes to make it maybe a little bit easier to manage. But now you can do this in any language. You can do this in Java if you want. In Java, well, as long as your functions can return functions. If you can write functions that return functions, if you can write functions that return functions, you can build your own curried functions. Since JavaScript can return functions, you can build curry functions. Java doesn't make it easy to return functions. So it's really hard to build curried functions in Java. Okay, it's probably a little bit easier in C++. C++, a function can return a function. In Java, it really can't. So in C++, you can build curried functions. In JavaScript, you can build curried functions, but you're still stuck with kind of an ugly notation. See, you can't just write F. You have to, when you call the curried function, you have to put in all these extra parentheses. Okay. Oh, once the function has been curried like that, I can't even use the so the function's curried, so I call it this way. Okay. I can't switch back to this other notation. See, what JavaScript did there, because it's kind of a flaky language, is it partially applied 3 to F and ignored the 4 and 5 and gave me back the partial. It gave me back the same thing as if I just said F of 3. See, it gave me back the same thing as if I just said F of 3. It ended up ignoring the 4 and the 5. That's just a quirk of JavaScript. Okay, so if I switch to curried functions and I hand roll the currying myself, I do the currying the hard way, I can get away with that in JavaScript, but then I have to call my functions always using this kind of quirky notation. But there are a small number of libraries I've seen that are doing that. I don't know if they would mention any, if they mention any particular see, here's the notation. See, that's what it looks like after you've curried a function. I don't know if they mention any libraries that do it that way. That if there's I think there are now getting to be some libraries that are currying the functions in the library so that you call them in this curried, you call them in this funny notation, but then you could do interesting things with the functions. ML, since it curries everything automatically, makes a lot of use of currying. It becomes very much a part of the language because you don't have to work hard to get it. You can just say function g is of x, y is x plus y. You don't have to write anything, and you automatically got a curried function. That's what they mean in modern sense when they say Haskell has a language with curried functions, or ML is a language with curried functions. Some people will argue, does JavaScript have curried functions? And the answer is, well, yeah, it does, if you're willing to write them yourself. If you're willing to do this hard work of, well, did I lose my, did I close the, I probably closed it. So I lost all that work I typed in. Can you get back your previous, does anybody know, is there a way to get back a console? Does it remember consoles? Does anybody know? I don't know if I can go back. Once you close a console, I don't know if you can go back to the console you had before. But
I don't think so.
Pardon me?
I don't think so.
Yeah, it'd be nice if you could go back to a console, but maybe you can't. Like this, if I close this window, I lose that console too. If I were to close this window, I'm going to lose everything that's in here. So here it's, yeah, if you close that, maybe you do, yeah, there's no way to get back to where you were. Okay, but Haskell will let you have curried functions, but you have to write them in the curried style. So you have to write them in this return function, return function, return. See, you have to do the currying by hand. So most people would say that Haskell, that JavaScript does not have curried functions, but you can go, you can argue with that. It does if you're willing to write them yourself, but then you have to use a new notation. Now you have to use this notation to call the function. Haskell, it's all automatic. Yeah. Haskell has what we would usually consider curried functions. It automatically turns every function of several variables into a function factory. So back to where, back to our MakeAdder, which was our first example of a closure, something that needs a closure, essentially a function that returns functions. So it's a function factory. The whole point of currying is that's just done for you automatically. And it's actually a brilliant idea. Okay, but it wasn't an easy idea to come up with. It does require this notation that gets rid of, it helps a lot to get rid of the parentheses in your notation. It's not crucial, but it helps a lot. Okay, so we're running out of time. We'll do a little bit more with this stuff. Like we're going to keep on talking about this idea of closures and function factories, because that's a lot of what modern programming is getting at. This is one of what people think of as useful in modern programming is the using of closures to create function factories. In this case, curried functions are function factories, and we'll see some other examples of function factories that aren't necessarily the same thing as curried functions. Okay, so, and then remind me on Wednesday if you have questions about, I forgot we were there's that programming assignment about the static analysis. On Wednesday, if anybody's got questions about that, we can start with that. Remind me at the beginning. So if you have a question about the static analysis program, we can start with that on Wednesday. Okay, because that's a pretty challenging assignment. So that's a little bit more challenging than the previous assignment. So if anybody's got a question about the static analysis and we want to talk about it, we can talk about that on Wednesday. Okay. All right. So meet again on Wednesday. Anybody have any last second question? Anything? Okay. All right. Bye-bye.